Hi all, this is Sangeeta who is working as an assistant professor in VSB Engineering College, Karur. And this lecture is about prefabricated structures. In this lecture, we will be dealing with the contents related to Unit 1. The syllabus which covered in this unit are need for prefabrication, advantages and limitations, principles of prefabrication, modular coordination, standardization, loads and load combinations, materials, production, transportation, and erection. So these are the contents which is available in this unit. The prerequisite subject, which is essential for better understanding of the subject, is concrete technology, building materials and construction, and structural analysis, and finally, reinforced concrete design. So these subjects will help you to understand better the prefabricated structures. And the course outcomes, which is covered in this subject, are first unit deals with the concept about principles of prefabrication, production, transportation, and erection. And the second unit deals with the panel systems, slabs, beams, shear walls, columns used in precast construction. And the third unit deals with cross-section design and joint flexibility issues. And the fourth unit helps you to understand about joints and also to acquire knowledge in connection in precast construction. And the fifth unit deals with structural stability. So there are preferred textbooks and references books are listed here. And this slide shows you the need for prefabrication. In on-site construction, we have weather delays and inconsistent site labor quality and sequential construction timelines, whereas in prefabrication, we have mass housing demands can met and accelerated project delivery, superior quality control, and reduced site footprint. So these are the advantages over. So this slide lists you the differences in casting 2 and prefabrication. In case of quality control, it is variable and site dependent, and in case of prefabrication, it is high factory controlled environment, and construction speed, it is parallel, that is site preparation and manufacturing can be happened simultaneously, but in case of cast in situ it is lower. And next one, labor dependency, it has a high manual requirement, whereas in prefab we can have skilled labors of minimum in number. Weather constraints, cast in situ depends on weather constraints and it affects the process, whereas in prefabrication it is a minimal site vulnerability. And in case of initial capital cost, cast in situ has lower initial and high initial capital cost for prefabrication. And in case of design flexibility, it is high and easy to alter inside, but prefabricated components has to be manufactured in standard sizes. And what are the core principles of prefabrication? Design for manufacture and design for assembly and logistics integration. So these are the three core principles of prefabrication. That is, standard components are easily manufactured and legally transported and instantly erected. It is the optimum prefabricated components motto. So that is, it has to be manufactured in a controlled environment and transported legally and instantly erected without any discrepancies. And here we can see about the definition of modular coordination. It consists of an important term called basic model. It is usually standardized across international cross section, for example, 100 or 300 increments, and it is represented in terms of a 3D grid system called XYZ coordinate system. It is used to define about the boundaries of the components, and actual component sizes or given some tolerances to account for joint thicknesses. Modular coordination assures you that whether the components are from different factories, they will align flawlessly for a particular structural component. And the next topic is standardization. It refers to the reducing of total number of unique component types in a building. It is classified into further dimensional standardization and connection standardization. And in dimensional standardization, uniform cross sections and lengths are used, and in connection standardization using identical joint configurations for every component length. And this image gives you an information about the light dynamic load shift from transient stage and service stage. In prefabrication, the critical design load case often occurs before the building is even construction. Engineered materials for prefabrication, and this slide gives you the details about the materials which are used in the prefabrication, and what are the applications of using such materials. In the high strength concrete enables rapid mold turnaround, and self-compacting concrete ensures dense compaction around a complex reinforcing without vibration. And also it is used for pre-stressing to reduce the component depth and weight, and high tensile steel strands used for pre-stressing to reduce component depth and weight, and non-string grouts which is used for filling structural voids at connection points, and also to ensure rigid load transfer. Elastometric materials which is used as a weatherproof in joints, and also helps in expansion and contraction. The materials mainly used are RCC, steels, rods on meshes, and elastomers, and grouts are used in case of joints. And this figure shows the production process of prefabricated component, and the first one is mold preparation and release agent is applied, and second process is reinforcement and hardware placement, such as reinforcement bars and screws. And the next process is casting and compaction, that is pouring and vibrating the concrete in a controlled and weather isolated environment. And next one, it is shifted for curing purpose. And the next process is after curing is done, and it is transported to the location where it is needed. And these are the constraints while transporting. First one is dimensional constraints, that is maximum width, height, and length can be dictated by highway regulations and tunnel clearances. And next one is weight limits. And bridge load capacities dictate the maximum tonnage of individual precast elements. And the next one is dynamic forces, that is the forces while transporting wind forces. Components must be designed to withstand such wind forces or lateral forces and vibration during transit. And next one is stacking logic. Elements must be loaded onto the truck in the reversed order of erection, that is last in is first out, so that it will be easy for placing the component. The next one is site erection. It consists of four components. First one is rigging and hoisting, which is used for lifting points to keep the element perfectly pumped. And the second one is temporarily basing is done. That is propping elements with adjustable steel struts before structural joints are grouted. And the third one is plumb and leveling using shims and modular grids for millimeter perfect alignment. And the next one is connections. So this is the process involved in site erection, and the prefabrication efficiency equation is that is in cast in situ construction, design involves 20% and massive site construction and problem solving is there, whereas in prefabrication, intensive engineering, coordination, and factory production is essential for an 80 percentage, and site erection is essential for a 20 percentage. So in prefabrication, 80 percentage of engineering, problem solving, and quality control must be resolved mathematically before materials ever arrived to the particular plant. So from this we can learn that in prefabrication, extensive pre-prior work is essential while fabricating a component when compared to cast in situ construction. And with this, we can end the unit one, which reviews the need and core limitations of prefabrication and the mathematical modular framework and dynamic load demands and the logistical life cycle from factory production to crane erection. And the next topic is prefabrication components and systems, which we will discuss in the upcoming lectures. Thank you.